Moving a servo is one of the first dreams everyone has getting into robotics. Being able to move a physical object through digital code feels like taming a dragon, commanding it to bend to your will. Servos can be connected to any extension you can imagine, sweeping arms 180 degrees or more, or rotating gears with acceptable precision. The only better feeling than this is controlling a digital servo in real time. What do you say? Shall we do this? The Tower Pro SG90 micro servo, like most hobby servos, operates with a 5-volt power supply at 20 milliseconds. Every 20 milliseconds, the servo is expecting a PWM pulse. We will need this frequency, so remember it. There are 3 lines that connect to a circuit board inside the motor: voltage, ground, and PWM. Equally important to the code you write is the schematic layout. We need to connect our power source to our chip. 3 volts is not going to cut it because we need to power the servo as well. You could use a separate power source for your servo, which is actually ideal. I try to get away with 1 power source because I like to keep things as simple as possible. If you are getting a slow-moving servo or it is jittery, it's likely your wiring and power supply that are the issue. Servos eat a lot of juice, so you need to feed them what they want. This is why I recommend a 9-volt power supply or having a separate power supply for the servo. The critical step to getting the connection working is to connect the servo ground wire with the chip's ground wire. They must share a common ground for reference. If your servo isn't working, make sure that you have this done. Now that our servo and power supply are connected, we are ready to get our hands dirty with the code. Before we go through the code, I want to suggest something that is going to help you become a better coder, and you're going to be able to do things faster and more organized. Instead of thinking of code as a once and done kind of thing, like you go through it from the top to the bottom and you type out all this code and you're done, think of it this way. You include the things that you know you're going to need one step at a time. So 1 block at a time is a better way to do it than trying to just plow through all the code. That's not how we build a house, right? You don't build the house in one swoop. You go in and you do the parts that you need to do. You lay the foundation, you go in, you put up the walls, you do everything you need to do, and then you put the roof on the top at the end. You don't try to just do it all at once. It doesn't make sense that way. So that's going to help you to feel less pressure when you're looking at code and when you're trying to write your own code. Here at the top, we have our preamble, and it looks very confusing to you, but I'm going to explain it and you're going to understand everything that's going on here. At the top, we need to include our essential header files. In this one, we're using the AVR IO, which is pretty much essential for every build that you do with these chips. And we're going to have our delay header file, which is down here. Here's this delay function, which is outlined in this header file that somebody has already done for you. So the first major thing to do is set up our PWM. We need to set up the frequency in order to communicate with the servo successfully. So here we have static inline void, and then we have a name that I made up, and then we have void. Don't worry about what this stuff means. It's not really important right now, and it's not really a big deal. Just copy what I have here, and you can give your servo whatever your PWM, whatever name you want. I just called it Timer 1 Servo just for organizational purposes. So this is going to be a 16-bit timer due to its high resolution and high speed, and it's the Timer 1 option in the ATMEGA328P chip. We're going to go into this register and we're going to flip on these bits. These bits set up the timer for fast mode in the 16-bit timer. The next bits we need to flip in this register are going to be for the prescaler. The prescaler divides our clock, which is at 8 megahertz now, and these bits, if you look at the datasheet, will divide the clock, the internal clock in the chip, by 8. And this makes it easier to work with. If we divide it by 8, instead of thinking of an 8 megahertz clock, we can think of a 1 megahertz clock, which makes it easier for us. Why is that important? For the next step. The next step is setting a top value, which is going to be our frequency, a top value that the clock is going to count up to. It's going to clear it out, and then it's going to repeat over and over and over again. You're probably thinking, what is this 20,000 value? Well, this little container right here, it's like a Tupperware container called ICR1. That's what they labeled it, so you just got to use it. ICR1 is the one that can hold this top value. Clocks and prescalers deal in microseconds. 1,000 microseconds is the same as 20 milliseconds. This was confusing for me at first. I hope this makes sense to you now. So 20,000 microseconds is going to be our frequency. So it's going to reach that value, and it's going to clear out. It's going to do what it's going to do, and it's going to reset and do it all over again. Next, we're going to go into data direction register B, which I covered in the previous video, and we're going to flip on pin PB1. PB1 is at the bottom right of the chip, and it's a PWM enabled pin by default. So this is my go-to for anything that I do with PWM. I just go all the way down to this bottom right pin. It's just really easy for me. So this just sets that pin to be able to output electrical pulses every 20 milliseconds. So after we outline this pulse width modulation timer 1 for our servo, we go down in here and we need to include it in our main. So this just calls it to the stage. This says, hey, that thing that we made up for timer 1, that 16-bit timer 1 for our servo, come into play. It's time to work. It's time to go to work. That's what that is. That's all you got to do. So that turns it on. So this outlines it. This actually turns it on. Next, we need to outline what we're going to do for the analog to digital converter. This is much more involved. It's a little bit more complicated, but once you start diving into this stuff, you're going to start to understand it, and it becomes really easy, really. Remember, it's all just flipping bits. So here we go. We're going to start off with static inline void. You don't need to know why. We'll do that later. I gave it a name called start ADC, and then you have these parentheses. And here's an open door and a closed door here. So this is going to outline how to set up the analog to digital converter. In the add mux, in the multiplier, it's going to need a bit to tell it what reference voltage to use. We're going to tell it to use the internal voltage flowing through the chip as a reference. It needs a reference voltage in order to do its it compares voltages, so it's going to need something to refer to. You can use an external source as a voltage reference, but we don't really need to do that for this one, so we're just going to tell it to refer to the internal voltage for reference. Next, in this ADC SRA register, we're going to flip on these bits. So this tells the ADC how many kilohertz to operate at. So remember, we pre-scaled our clock to 1 megahertz. We divided by 8, right? So we're going to need to keep that in mind when we do this pre-scale. So we have the 1 megahertz clock, and we're divided by 8, which gives us a mid-range value of 125 kilohertz. The ADC functions between 50 and 200 kilohertz, so if we divide it by 8, it gives us this nice mid-range value. This sounds confusing. It's just something that you have to do in order to set up your ADC. Next, we're going to move on to the enable ADC bit. This actually tells it to turn on, so make sure you include that. Next, we're going to start to implement it in our code by coming down to the main and calling it into action, just like we did with our PWM. So here's the actual call for that to come into play and to turn on in this fashion. Next, we need a way to read out the values of the ADC. So we have the ADC set up. Now we need to figure out how we're going to get this to work. So this is code that I borrowed from Elliot Williams' book that I always recommend. It totally made this all possible. I couldn't get anything in my head if it wasn't for his book. So I highly recommend you go and check it out. There's a link in the description. So we're going to use a 16-bit integer in order to read the ADC. Remember, the ADC puts out 10-bit values shared over 2 bytes. So 2 8-bits. So it simulates a 16-bit number. So we're going to use a 16-bit variable called read ADC. And it's going to refer to an 8-bit thing that we're going to call channel. You can call it marshmallows. It doesn't matter. You can call this, Yankee Doodle. It doesn't matter. All right, so this is going to be the actual pins that it's going to be looking at. It's going to be listening in on different pins, and it's going to read that value and store it as a 16-bit variable. So here we go into the ATMEGA again, and we say turn on the 4 out of the 8 bits. So if this was FF, this would have been turn on all 8 bits, but this is 4 of the 8 bits. I'm not going to go into specifics of why we do this, just copy the way it is. The multiplier is a very complex topic for another video. And we're going to say to refer to the channel. So it's going to flip through channels 0 through 6. If you look at the ATMEGA328P, you'll notice it has ADC 0 through 6. These are the different channels we're going to tell it to refer to. So we're going to have channel 0, 1, 2, 3, 4, like that. Next, we go into this register and we're going to flip this bit called ADSC. This actually starts the conversion. Analog to digital start conversion. So we're going to flip that on. We're going to say, hey, go to this channel and start the conversion. Inside the analog to digital converter, there are certain flags and bits that clear out once the work is performed, once it's done. So we're going to tell it to start the conversion and be in that state. We're going to loop it until this bit is clear. What bit? Well, in this ADC SRA, so in this serial register A, or status register A, we're going to tell the ADSC bit that it needs to be clear, and then we're going to return the ADC value. So once again, this is very complicated. If you look at it, if you watch this video over and over, you'll start to understand it. So now that we have this all set up, how we're actually going to read the values in, we're going to come down here into our loop. The loop is fairly simple. It's going to look complicated because you're not familiar with these terms, but actually this is very, very, very simple. Most of the hard work is in the setup of this entire code. So in the loop, we have an open bracket here. So we have a closed bracket for the loop and for the main. So keep that in mind. This is the closed bracket for the loop, and this is the closed bracket for the main. We're going to have a 16-bit variable that we're going to say X because it's the X axis. You can call it A, B, C, D, whatever you want. You can call it a name. Basically, we're going to create a 16-bit integer. I deleted the Y. We don't need the Y. Basically, we're going to create a 16-bit integer value for the ADC 10-bit values coming in. So this is just going to store whatever value is coming in from the ADC. We're going to set that to be equal to whatever the ADC reads on channel 0. That's what this is right here. You see this? Read ADC, channel. So if we tell it to read channel 0, that's ADC 0, which is pin PC 0. So this will start to slowly make sense in your mind. And then we go into OCR1A, which is PB1. If you look at your pinout sheet, you'll notice that OCR1A is attached to pin PB1. So we set OCR1A to equal whatever X is, whatever the analog to digital converted value is, and we're going to multiply it by 3.5. I did this because it just helps with resolution. Play with this. Play with this. This is going to vary the resolution that's coming out on your pin because you have this ADC value coming in, we need to change the ADC value in order for it to send out a pulse of between 1 and 2 milliseconds. If you just do it as X, if you just set it to X, it's not really going to work. You can try it out and you'll notice that it doesn't really work because it's not scaled correctly. The ADC value needs to be translated. It's not going to be perfect. You'll notice you get these values in and they're not big enough. So that's why I multiply it the way I did. And you can play around with that, and there's different ways to do it. This is just the way I like to do it. All right, and make sure you close it out with the return 0 and check all your doors. Make sure they're all closed, all the doors you open, and that's it. That's all the code. We have our ground coming into the chip, and we have our voltage coming into the chip. Next, let's hook up the servo. So here we have our servo. Remember the brown is the ground, red is voltage, and the yellowish, orangish is the signal wire. Signal's hooked up. Next we got to hook up the ground and the power. I'm just going to connect this to the same wire here, and we're going to hook up the ground, the same rail, so we can share it. Okay, so I'm just going to go ahead and connect our ground. The servos our servo is looking for a signal to come in, so we're going to have to hook up our joystick. You can see what color scheme I'm using. For ground, I'm going to use black again. For 5 volts, red again. And then for our X-axis, I'm going to use this yellow wire so I don't get confused. Okay, here we go. It is hooked up. Okay, it looks like a mess, and that's why a lot of people like to just cut their wires. These are the DuPont wires where you can pull them back out and plug them in wherever you want. Some people, once they get it all down or they know their schematic really well, they like to cut wires to size and make it fit perfectly on the breadboard, and it looks really nice. You can do that if you have patience. I don't, and I like to do that later when I actually solder something to a board. So here you go. This is the servo, and this is the joystick. And to prove that it works, do a little demonstration. So remember, we haven't plugged in the Y-axis yet, so it doesn't move. It doesn't move with the Y-axis. If I move it to the left or the right, it's gonna move. And watch this, look. You can see the kind of resolution I get by slowly sliding it. So remember, I did a little math, just simple math to get a little bit different resolution coming out of this thing. But you can do whatever you want. That's the great thing about this. You can figure out different ways to get better resolution, and there are better ways. This is just an easy way to get you up and running and start thinking about stuff and playing with stuff that you can build. So what can we do with this thing?